To map the behavior of quantum systems or the dynamics of complex fluids, physicists rely on linear operators. But these operators function in infinite dimensional spaces, making their complete structure incredibly difficult to chart. This chart shows the complex plane representation of a linear operator. It is divided into two strict territories. The open area is the resolvent set, where the operator has a clean, well-behaved inverse. The central region is the spectrum, the danger zone, where the operator cannot be simply inverted. In finite dimensions, this central spectrum would consist of a few isolated points, known as eigenvalues. Infinite dimensions, however, allow for continuous and residual spectrums. These are entirely new mathematical regions, where an inverse might exist, but is unbounded or strictly limited in scope. When you try to solve an infinite dimensional equation, you have to know exactly where these boundaries lie. Attempting to invert an operator inside the spectrum causes the mathematics to break down entirely. The open space outside the spectrum is governed by strict rules. The resolvent equation shows that if you evaluate the resolvent at two different points in the complex plane, mu and lambda, the difference between them is exactly proportional to their product. The proof for this relies on a specific algebraic substitution. By inserting the identity operator into the terms, we maintain their value while giving the equation the structure it needs for the next step. These identity substitutes allow us to factor out the resolvents on both sides. All that remains in the parentheses is the difference between the operators themselves. Because the difference between those operators reduces to a simple scalar, mu minus lambda, the order of multiplication does not matter. The resolvents at any 2 points perfectly commute. The values in the resolvent set are not isolated points. The inverse of the operator at one location is algebraically locked to the inverse at every other point in the open plane, forming a highly structured, interconnected web. According to the spectral mapping theorem, this geometric structure holds up even when we modify the operator itself. If you apply a polynomial to an operator, you apply that exact same polynomial to its spectrum. Take a spectrum that lies between 0 and 1 on a number line. If you square the operator, the spectrum is squared too, mapping perfectly back onto that exact same interval. We prove this by breaking the polynomial down into its roots. The expression becomes a chain of individual linear factors, all multiplied together. For the entire polynomial to have a valid inverse, every single link in this chain must be invertible. If even one factor hits a point inside the spectrum, the inversion fails for the entire product. Algebraic lottifications to an operator are perfectly translated into geometric distortions of its spectrum. You can map exactly how the boundaries will move without having to recalculate from scratch. We can analyze the resolvent exactly like an operator-valued function. As we move our variable lambda through the open resolvent set, we are moving a physical point closer and closer to the boundary of the spectrum. Because the resolvent is a holomorphic function, it can be represented as a power series. That series converges perfectly within a circular radius, expanding right up until its edge strikes a spectral value. There is a strict mathematical relationship between the size of the resolvent operator, its norm, and its physical distance to the spectrum, known as delta. As delta shrinks towards 0, the norm of the resolvent grows inversely, spiking upward. The geometric boundary of the spectrum represents an absolute mathematical barrier. It is the exact threshold where the operator's inverse violently explodes to infinity. To prove the spectrum is never empty, we observe the resolvent's behavior at the edge of the complex plane. As our variable lambda grows toward infinity, the norm of the resolvent operator shrinks toward 0. If an operator had no spectrum at all, the resolvent would be defined everywhere, meaning it would be an entire bounded function. By Liouville's theorem, such a function must be a constant 0, but an inverse operator can never be 0. Therefore, a non-empty spectrum must exist to bound the function. Because the spectrum exists, we can measure it. Gelfand's spectral radius formula determines its absolute outer limit. By calculating the algebraic limit of the operator's norm raised to a sequence of powers, we find the exact radius of the smallest circle that can contain the entire spectrum. This abstract mapping is what allows us to calculate energy. In quantum mechanics, the states of a system are represented by vectors, and the discrete energy levels we actually observe are the specific points found within the spectrum of the Hamiltonian operator. Furthermore, to solve complex boundary value problems in continuous physical systems, physicists rely on Green's functions, tools constructed directly from the behavior of the resolvent operator. The resolvent and the spectrum turn the abstract problem of finding an inverse into a geographic study. They allow us to predict exactly where a mathematical system remains stable and where its underlying operators will inevitably fail.